In our previous set of lesson videos, we covered some of the fundamental concepts that we need for determining probability. And in this lesson, we'll actually begin to cover the rules that govern how probability works. Our aims in this particular video will be to describe probability and what it applies to, and then describe some of the most basic mathematical rules that define the probability of complex sentences. We talk about chances all the time. The chance of rain, the chance that a candidate will win an election, the chance of getting struck by lightning. And we're going to look at a way of formalizing these chances. We're going to talk in terms of the probability of statements. Remember that statements are declarative sentences that are true or false. And that will be important because some of the logical formulations that we've used from truth functional logic will be relevant again here. So we can use sentence letters to stand for sentences of English. So P could stand for it will rain tomorrow. And then we have PR parentheses P and parentheses. That's our probability that the statement P is true. The probability that it's true that it will rain tomorrow. Most of the time we'll talk in shorthand, so instead of saying the probability that it is true that it will rain tomorrow, we'll just say the probability that it will rain tomorrow. And while we'll focus on characterizing probability in terms of statements, be aware that it can also be described in terms of events. And when we use that kind of description, we use sets as our formal tools. But for our purposes, we're going to use statements and the connectives of truth functional logic. The mathematical theory that describes what probability is and how it works is called the probability calculus. The rules of the probability calculus tell us when and how we can determine the probabilities of complex statements from the probabilities of simple statements. The probabilities of statements will always range between 0 and 1. That's our basic rule of the probability calculus, and it applies to all statements, whether simple or complex. And what do we mean by complex statements? We mean the ones that can be built up from simple sentence letters with our familiar logical connectives. Disjunction, conjunction, and note we have a new symbol here, so sometimes we can use the hat and sometimes the ampersand. Both of those stand for conjunction. And then negation, we have the bar or the tilde. Either of those would work. Let's illustrate what we mean by the probability of simple and complex statements. Just like we did in truth functional logic, we're going to use single letters to represent our simple sentences. So for example, we can represent the simple sentence, it will rain, with the sentence letter R, and the probability it will rain as PR of R. So if the chance of rain is 70%, that's the way we would ordinarily say it, we would write that PR of R is 0.7. The rules of probability constrain what the probabilities of simple statements can be, so they have to be between 0 and 1. But our probability calculus does not tell us what the probabilities of simple statements are. Those are determined by what the facts are in the world, and we have to infer those probabilities in various ways. For example, the probability that it will rain tomorrow, PR of R, how do we get to know that? We use meteorological models and our knowledge of the equations that capture atmospheric dynamics, and data about current conditions. All of those allow us to arrive at a probability number for the chance of rain. We're not going to be doing meteorological modeling. Our interest is in how the probabilities of complex statements can be dependent on the probabilities of simple statements. So a complex statement built from two simple statements and a logical connective is something familiar, like it will rain or it will snow. Sometimes we want to know the probability of these kinds of complex statements. So we see on the upper right how we would write that. The probability of R or S. The mathematical rules of probability tell us how and when the probability of certain complex statements can be determined from the probabilities of the simple constituent statements. In some cases, we need to know more than the probabilities of the simple constituent statements, like R and S, to get the probability of the whole complex statement, and we'll see that in upcoming lessons. But for now, we're going to look at 3 rules that govern the probabilities of complex sentences. One for tautologies, one for contradictions, and one for equivalent sentences. Our first rule tells us the probability of any tautology. Doesn't matter how complex it is or how many logical connectives it has. If the sentence is a tautology, it will obey this rule. So remember that tautologies are sentences that are guaranteed to be true. The first rule of our probability calculus is that if a sentence is a tautology, its probability is 1. So if P is a tautology, then PR of P equals 1. What that probability number tells us is that it is certain that that sentence is true. And that's what we should expect, given that the sentence is a tautology. It should be certain that it's going to be true. Take this example. The sentence P or not P is a tautology. We can demonstrate that in a familiar way with the truth table shown here. You can see that the sentence is true, as marked under the main connective there in red. No matter whether P is true or false, the sentence P or not P is true. That makes it a tautology, so the probability that P or not P is true equals 1. There's also a rule that tells us the probability of a contradiction. Remember, that's a sentence that's guaranteed to be false. Again, regardless of how many connectives it has or how complex it is, if it's guaranteed to be false, it's a contradiction and it will obey this rule. So if our sentence P, where that can stand for a sentence of any degree of complexity, if it's a contradiction, then the probability of P is equal to 0. This tells us that there's no chance that the sentence is true. And that makes sense, since a contradiction is always false. So the sentence P and not P is a contradiction, and again we have our truth table that proves it. The sentence is false no matter whether P is true or false. So given that we can show that this is a contradiction, the probability of P and not P is equal to 0. Our last rule for this lesson video applies to equivalent statements. Remember that statements are equivalent if and only if the statements are true in all the same circumstances. So our next rule of the probability calculus tells us that if P and Q are equivalent, then the probability of P is equal to the probability of Q. So since equivalent statements always have the same truth values, the probability that those statements are true has to be the same. So we don't know what the probability of these statements P and Q are, but whatever the probability is, it's the same for both of them. So take our example below. The sentences not P or Q and not P and not Q are equivalent. You should maybe remember that from our De Morgan's rules, and we can show it with the truth table here for good measure. Both of those statements themselves are contingent. Sometimes they're true and sometimes they're false. We don't know what the probability of either of those complex sentences is. That will depend on what the probabilities of P and Q are and the rules for combining them with conjunction, negation, and disjunction. But whatever the probability of not P or Q is, it has to be equal to the probability of not P and not Q. Whatever number that is, it must be the same. And with that, you have some of the most basic rules of probability. And in the next couple of lesson videos, we'll cover additional rules for complex sentences, ones involving conjunction, disjunction, and negation. And in particular, how to calculate the probabilities of complex sentences based on the fact that they contain those logical connectives, instead of based on whether or not they have properties like equivalence or being a contradiction or being a tautology.